Hello. I'd like to take a few minutes today to go over a short tutorial on how to use a couple of tools that we produced here at Thunderhead to help you calculate t-squared fire data in addition to a little database of previous fires, profiles that have been gathered from various fire experiments. And both of these tools help in different ways to give you the heat release rate curves that you're looking for your design fires. In addition to that, I'd like to demonstrate how to basically freeze the heat release rate when a device activates inside of your FDS simulation. And then finally, how to use the activation of the device as a trigger to shut down your simulation. So we've got a bit to cover here, but hopefully we'll go through it fairly quickly, and this will be very helpful if you're ever doing design fires in FDS and need some tools to help make that process easier. So first thing that we're going to do is just a quick review of the model. I'm going to get into a few of the details here. This is the complete model, and so I'll be talking about the various points here. And so let's go ahead and start with the mesh. It's a fairly small mesh. This is just for demonstration so that we can get through the simulation quickly. One thing to note is I did open up all the mesh boundaries, but I pulled the tops of these open vents down just so I can get a little bit of a header to help build up the heat in this upper layer to help activate the sprinkler earlier. So this is a little bit contrived just to help with the demonstration, but I wanted to make a note there. That's why it's sort of collecting heat up in this upper level for that sprinkler. And this is not using a sprinkler, so there's no nozzle with spray. If you look in the devices, you can make a sprinkler link, and you can also do that through the toolbar. If you click on the device here and right-click and go to Tool Properties, you can pick the device type as a sprinkler link. You can also do heat detectors. You can do various device types here. I'm going to go a sprinkler link because I do want to use this general sprinkler link model that does include the RTI and the activation temperatures. I did modify this slightly from the default. I did put it at 50 just again so it would activate a little bit sooner than the default. I believe it's 74 C. So there's just a little lower temperature for earlier activation. And name that sprinkler link. We put that at 2.8 meters above ground. The ceiling height is at 3. And now you can move around and drop a new one in. I'm just going to escape. I already have one of those. So the next part of this model is we'll go ahead and just talk briefly about the fire vent. I did make a burner. So you can see this burner surface type. So you just do new, type burner, and you want to put in the numbers here. For this heat release rate per unit area, we've got 1,000 kilowatts per square meter. That is something just to note. Depending on the area of your vent, you may have to scale this value to get the proper peak heat release rate that you want. The tools that we have assume the peak heat release rate as it is, at whatever kilowatts it is. But this number is normalized by area. So you're going to have to make sure that you scale this number based on the area of your vent and not just use, if I say, for example, my peak heat release rate is 500 kilowatts in the model, I may not put 500 kilowatts here if this is not 1 square meter. If it's larger, I'd have to bring it down. If it's smaller, I'd have to increase this, to get that target of 500. So you can scale it by the area. The next part is now I have a custom ramp. And so normally when you come into a ramp function, this is set to time. You have your time column is clear. And in fact, I'm just going to delete all of this. Let's see if I can pop that all out in once. Yep, remove row. We'll go ahead and say, okay, I got to have at least one. Let's go 0, 0, because I just want to demonstrate this. We'll go ahead and say okay to that. And I'm going to set this back to default. So this is usually how you come into the edit surface dialog. It'll be a default of 1 second for the growth. We're going to be using a custom ramp. Now, you can also use the t-square, but unfortunately with that, it doesn't provide any kind of delay built in. It doesn't let you know how long you want to maybe stay at steady state and then what your decay phase is. And so a lot of people will want more than just the basic t-square that grows up to the peak and then stays there. You want something that's a bit more like these curves. So we have some delay time, some growth phase, some steady state phase, and some decay phase. This is our older heat release rate calculator. This is a data-driven one where we actually have a little data page. And you can see here that some of this data was pulled from some experimental results where these numbers were quantified. But a lot of the times when you're doing a design fire, you don't necessarily know the entire history. You don't know the time history of like, well, when does it start to grow? And then when does it actually hit peak? And then when does it start to decay? And then how long? Because you need to calculate these curves to get the timing right. You've got to follow the growth curve. So what I did then was put together a little bit of a different spreadsheet here. And so what this one does is it calculates for you the entire curve based on a known heat release rate, your peak. So let's go ahead and say 1000 here, and your initial delay time. So that's 10 seconds I want in the beginning. And then a growth rate on my growth phase. So we have a few standard alpha values that you can pick from here. Makes it pretty quick. I'm just going to copy the fast. So I'll copy that, and then you can come up here, and I like to just right click and paste values. And so I can get that growth side. And then how long do I want it to stay at peak? We'll say 20 seconds in this case, and then it begins to decay. And we'll say that it decays ultra fast, has a nice quick burnout. And I'll go ahead and paste that, just the values, and we get that paste there. All right. Now, the next set of parameters are your simplification parameters. So what these are is how many points do you want to use to define the growth phase and the decay phase. Everything else is just pretty easy. You have your time 0, you have the time after your delay. The delay can be 0 if you want, and that would just be 0, 0. You then have your start time here, and then this number of points. So whatever you set this to will define how many points are used to define up to the peak. And then your peak time, your beginning of your decay time, and this just holds steady at whatever your peak is. I haven't calculated it yet, so it's a little bit different here. And then your decay side. So from that peak down, how many points down to 0? So if we go ahead, I'm just going to do 4 and 4 here to make it a smaller table. And that's all you really need to input is these first two tables of what you know, and then you click calculate curve. And then what it does is it goes over time every second and it computes the values, and then based on your curve. And so you can verify here, that I have my growth and my decay and my timing and everything is all determined for me. And then the second column, this is where it uses these simplification parameters to take this raw data and trim it down to a smaller data representation, which is reflected by the simplified line you can see here. And you'll notice that, especially in some of these areas here, that there's a small gap between the blue line, which is that raw data every second, and our simplification line, which is, only 4 points in this case to capture that curve. And you may wonder, like, well, what's my error? Like if I use this simplified data, how far am I off for my energy? So if we take a look down here in this little yellow table, we'll see the raw data is how many megajoules, and then the simplified data and its number of megajoules. We can see that's a bit higher than the other. The difference is about 1.94 megajoules of energy difference in our simplified, and it's to the positive. So it's about a 1.02% difference, an increase. So it's relatively small. That's close enough to, it's close enough for what we're trying to do here. And it still gives us relatively simple set. If you add more points to this, then our simplified set will get closer to our raw set and this difference will decrease. So you can continue to refine that. If 1.02% difference is too much in the area under the curve, then feel free to refine that further if you like. And then at the bottom here, you can see we have this little blue table of curve data. And so this curve data is pretty useful because these variables actually fit right into the table over here. So I put those numbers in. You can just take those right from it, give it a name, give it a description, put the numbers in that you need for all of your parameters, and you can save that into this file and reuse your calculation for that curve later from the other database. So now we have a curve. Let's go ahead and grab this. So we have time, and we want the normalized. This is, from 0 to 1, using a normalized or a fraction, in this case, of the peak values. We can also just verify these are the actual heat release rate values over time, and this is that normalized as a fraction of the peak. So we'll grab those, and then let's go back into PyroSim, and instead of using a t-square like this, we'll go to custom. We'll edit the values, and you can just click into this first cell and Control V and paste those in, and we get that data from our spreadsheet. So as it is right now, the heat release rate from the burner will be released based on this fractional value over the time period. So this is kind of linear interpolation between 0 and 10, 0 to 46. It will grow at a linear fashion between these points. And the input to this function is time. And that's real simulation time. We don't want that, okay? And I'm going to go ahead and say okay to this for now because I want to point out these other tools that I've set up, a couple other devices. So what I did is I went over to device and I added a new time device. And so let's go ahead and open that. I called it HRR time. And it is measuring the quantity of time and reporting the quantity of time. And if I didn't have any kind of freeze here, it would just, for every second in the simulation, it would report the time back exactly as it is in that point in time. But what you can do with a time device now is I can freeze this time. So what I then did is, usually this will say never or something, right? So I made a new control. I called it freeze time. And let's click into that and see what it does. And it is a detector that is going to freeze. That's the action it will perform. So it'll freeze HRR time when Sprinklink 1 activates. And so that's my little sprinkler link that I've defined when that activates. And I wanted to delay that freezing by just a little bit. I'm going to delay that by 20 seconds. Oh, actually, no, I'm going to leave that alone. Sorry. Just put 0 in there. Okay. So as soon as that sprinkler link activates, I want to stop increasing, or you can almost say like measuring, reporting the simulation time as an output of the time device. I want it to hold whatever value it was at when this activated, just hold that number and report it. So what's great about that now is I can go into my burner. Let's go ahead and pop back into the burner here, and we can edit values. And what I'm going to use is for this time column, instead of using simulation time, I'm going to use that heat release rate time device. And so as it's going up, as soon as the sprinkler link activates, let's say that happens at 90 seconds, then whatever this fractional value in that linear interpolation will be between 82 and 118, when it's at 90, it'll just hold that fraction and just keep it. And it'll keep reporting 90 for the rest of the simulation. And so that'll hold the fraction, this constant, and we'll get a leveling or a flattening of the curve. Basically, this shows an assumption that when the sprinklers activate, they can hold the heat release rate at where it is without extinguishing it. It's just kind of a conservative, we maintain where it is, we don't diminish it or let it increase. So that's what we're doing there. And we don't have to use particles or droplets or extinguishing coefficient or anything else. We can just make this assumption and move on. So we'll go ahead and say okay to that. And now our burner ramp is using heat release rate time as the input to it, and will freeze when the link activates. The next thing that I added was I went to the devices here and I added a sim control device. And there are a few different sim control device types. You have 2 options to kill the simulation, which it's a little extreme there. It actually is the same as doing a stop. It's not like killing the simulation, like killing the process. It actually does a graceful shutdown, but it does stop it. And then creating a restart file is the other option you have. And that's great for using some kind of sensing or some activation, something happening in the model to just take a snapshot and something you could roll back to if you needed to at a later time with a restart. So we're going to leave this alone. I'm going to cancel that because I've already created one of those. And then what I did is, so I made the sim control and I set its activation. I made a new control called shutdown. And let's go ahead and take a look at that. It's also a detector that activates. So we're going to activate the sim control, which is this device, when Sprinklink 1 activates. But in this case, I do want to delay by 20 seconds. So after it activates, I just want to let the simulation run for some amount of time after activation to get that kind of capture that steady state for a bit, and then go ahead and shut off, stop the simulation. So we'll go ahead and leave that alone and okay to that. So you can see I have my Sprinklink. I've got my heat release rate time, which is a time output device. I've got my sim control, which is going to shut it down when the sprinkler link activates. I've got 2 controls. I have a freeze time control, which is just set up to stop updating heat release rate time output when the sprinkler link activates, and a shutdown, which will activate the sim control device when 20 seconds after the link deactivates. So I have everything I need now in the simulation. What's really nice about the setup now is I can go to the simulation parameters and I can just set this number to something really big. I set it to 1,000, 5,000 seconds, doesn't matter, because it won't run to the end time. It's only going to run until 20 seconds after activation, which is really great if you're using cloud computing, anything like that, and you want those processes to shut off and quit charging you money when it's done. You can use that sim control device to stop it some number of seconds after some critical event has happened. So if you define, some kind of failure criteria or something in your model, if the temperature of the surface exceeds a certain value or whatever, you can then tie the activation of that device to the sim control device through the control and have it shut your simulation down and not waste any time or CPU cycles on that. So we have everything we need. Let's go ahead and run it. I'm going to fast forward for a little bit as this runs just to save some time in the tutorial, and we'll be right back to continue. Okay, so it looks like we've leveled out here, and we now have a flat line much earlier than it should be. Based on our heat release rate curve, we could compare this curve and just make sure that we got a matching heat release rate over time as we predicted with our calculated one. But we can, let's go ahead and take a look at some results. So all I did here too, by the way, is you can pull this little tool down, go to thermal results, and then over time, if you want, you can, pick whatever you want, mass loss rate of fuel. So we saw that here, heat release rate, we see that here. And then as it's running, if I just hit F5, so it's refresh, it'll just pull in the latest data and keep updating this curve. So it's a pretty nice way you can just kind of periodically hit F5 while it's running and just see where you're at with your curve. You can also do the same thing. If I pull this little arrow down, I can do the same thing with the device results, and I can see here my link temperature. Remember that my target was about 50, so somewhere around here it activated, and then it just continued to rise as we got that last 20 seconds or so of the simulation. And here's the heat release rate time, and we can see it going up at a 45-degree angle as we would expect, because time output is reflecting time input. But as soon as we get up to this point in time, it levels out because we then froze the output of time over simulation time. And so we see the effect of that freeze function on that heat release rate. So let's go ahead and here, we'll take a look at our results. Okay, so we've got a couple of things to show in here. The first thing is I did make a 3D slice through the domain. So you can add the, would any kind of volume that you want within your simulated domain, you can define a 3D slice through that. And in this case, I have temperature. So I'm just going to drag this forward in time, and we see a cloud of temperature, kind of a volumetric cloud. What's really great about having this kind of data is I can extract things from it. So if I right-click temperature, and let's say we add an isosurface, and I'm really interested in that 50-degree threshold that I mentioned earlier. Let's turn off the cloud, and now I can see this animated isosurface that was extracted from the 3D data. I didn't have to generate that or ask for it from FDS up front and have it write it out. I can later come back and just add that visualization in to the 3D volume data. You can do the same thing with points. You can also add 2D slices through things after the fact, because you're really just extracting data that you have in 3D to a 2D plane, an isosurface or a point device. And what's really cool about point devices is that you can then further, if I add a point somewhere in space and I get that data, then I can right-click this. I can export that data to CSV if I need to evaluate it. I can also show a plot of that data over time from that point in space. And it's just, again, sampling. Let's go ahead and show the markers off. It's just sampling data from that point in space over time from the 3D volume. So I'll delete that. Let's grab our plot data too. So let's go to the CSV file here. So we go to XY plot data. Let's get our device data and our, heat release rate. Let's do that one first. So we'll go ahead and open that. That should then identify that this is a heat release rate or FDS thermal output. Great. I now have a new area here. I have all those plots, those things that I was looking at before. Let's go ahead and show this plot, and I will turn off data markers here. And so now I have heat release rate, and as you mouse over, you can look at the values. Kind of gives you a little pop-up on that. You can change range. I can double check the curve. I get that initial delay for the first 10 seconds or so, and then it takes off and goes up and ends up leveling out when the heat release rate freezes. And I can check that out with that reaction fuel. So let's double click this, same deal, right? So this is really what's happening behind the scenes. This is the mass loss rate of fuel, and you can see when it gets to that activation point, it stops growing, right? And so I'm just releasing the same amount of gas fuel from the burner over time and holding that heat release rate steady. So hopefully this is all very helpful. It's kind of a quick demo here, but hopefully these tools are useful. You can use them to calculate your curves. You can put in any numbers, save them with your project. You can add to the database here by calculating curves, and then go ahead and use those in your FDS simulations and for your design fires. So if you have any questions, please email support@thunderheadeng.com, and have a great day. Thank you.